talk about Gridworld and take it as a big picture. This is on the AP Computer Science A test, and it will have anywhere from 5 to 10 multiple choice questions and 1 free response question. So you have to be familiar with its classes like bug, box bug, critter, chameleon critter, and how they're implemented. So how do you remember all that? You don't. You have to just know how to find the documentation in the quick reference guide. That's an important thing because it has all the methods listed out, and it has some source code, at least for the bug, box bug, and critter and chameleon critter classes. It doesn't have everything, but it's got plenty. So make sure when you get to the test, they think it's fair game to ask you about how each of those classes are implemented. So you'll have to know all of the members of the classes, all the methods, and how it works and functions. You have to know how to call any of those methods, and you have to understand what happens, the preconditions and postconditions of all those methods. And the reason why is because you're going to be able to alter the behavior code by just changing the behavior of perhaps overriding one of the methods or adding attributes to a subclass and using inheritance. And so you need to know everything in the API for Gridworld, enough at least to make your own bugs and critters and such. So here's an overview of the classes. Most of these things that we're talking about, flowers, rocks, and bugs, have a lot in common, so they're a subclass of a more generic actor. Actors are designed to live in some sort of world, like actor world, and usually that's on a bounded grid or perhaps even an unbounded grid, which are implementations of a more abstract grid, which itself is uses the grid interface. We're going to be using a lot of the we're going to get the instance of an actor's grid so we can use some of these grid methods. One thing that we don't ever really need to change, but we definitely need to describe location, so we're going to be using location class. Actors need to know their location, and of course grid uses the location class too to describe each of the cells, the rows and columns. And we're going to be making subclasses, usually of bugs and critters, and see how altering some of the methods will change the interaction when we animate them. Well, talking about animation, this is probably the opposite. Rocks do nothing. It's listed in Appendix E, so take a look also in B4. You won't actually get to see this code during the test, but here it is. They have a default color of black, and there's 2 constructors here. If you don't specify, it'll be the default color. Otherwise, you can send a parameter to the constructor about a particular color you want. And finally, of course, the act method that does nothing. Let's take a look at something more interesting like flowers. Here's a flower on a grid. Good to mention that grids are located by row and column. This is the 0 row, first row, and this is 0, 1, second column. And so the way we describe the location that this particular flower is occupying is 1, 2, because it's in row 1 and column 2. Flowers do have a little bit of act. They don't actually move, but they do darken. And here you don't need to know this code for the test. But if you want to make your own stuff that darken, it just changes the color by reducing the amount of its current color by a certain darkening factor, and sets that color to that darkened adaptation of the old color. And that's how they fade to black, quite literally. You also don't need to know some of this graphic user interface for the test, but while you're working on your own bugs, preparing for the test, it's good to know how you could select a location and delete to remove something on the grid. You can always do a right click and add things as well, but there's keyboard shortcuts like pressing the enter key and also using the page up, page down key that a lot of people don't realize. And of course, Control Q certainly is, or a Command Q if you're on a Mac, it's another way of quitting the grid world. Alright, finally, something that moves, bugs. So they try to go forward, or actually I shouldn't say forward, they go in the direction that they're facing. So if they're facing north, they'll try to move to the location north of them. If it's east, they would go to the location east of them. They don't go off the edge. You just are forced, like confronting a rock. So if they're blocked like an edge or a rock or another bug, it'll try to turn, and it'll turn to the right 45 degrees. Take a look at C1 and C2 for more info. Here I'll have at 5, 5, counting from 0, the bug is here facing a rock. Box bug here is facing another rock, and of course the critter is also facing a rock. The movement is these will turn, but the critter can go to any of the other unoccupied locations. So let me just press a step. So the critter has just successfully moved away from the rock because it shows randomly from its neighbors. The bug, because it's a bug, will turn to the right 45 degrees. So it's now going northeast. But the box bug always turns at right angles, so it's facing due east. We'll press one more step. And here the critter will eat anything in its path, but it doesn't eat rocks and it doesn't eat other critters, but it will go to any of those random locations. The bugs, because they're able to move, drop to flower. The flowers don't move, but they do darken on each step. You can see some darkening. You notice that the bug here had to turn another 45 degrees since it couldn't go up and over. It found an edge. And the box bug turned either because of the edge or because the box is only 2 flowers wide or 3 flowers wide. Here we'll see finally the critter will eat this flower because finally in its neighborhood there's something other than a rock. And then it moved away in a random location from its former location. We notice that the box bug turned even though there wasn't a rock, and that's because a box bug counts a number of steps, and it will turn the direction, now it's going north, to make a box if there's nothing in its path. Meanwhile, the bug keeps going. Notice that the bug will go ahead and replace itself with the previous flower, so the flower just goes away. Notice that the box bug turned again because it got its length, 1, 2, 3, 4, 5, 6 steps before turning. And this critter will eat these 3 flowers because they're neighbors of the critters, so they'll just go away. Here it'll eat one more flower and it bounces away. Finally, the critter gets to eat a bug because of these neighboring locations. There is a bug in it, so it will be consumed. If we just let this continue, eventually now it'll consume the other box bug, and eventually it'll dance around eating everything but the 3 rocks. But that might take a while. Oh, not too bad. So the box bug, the yellow one, it's designed so it turns at 90 degrees, and it has 2 new attributes, steps and the side length. So every time it moves, it counts up another step until it can't move anymore or it's exceeded its side length. Very important demonstration because bugs have a turn method. One way to reuse code is rather than setting the direction directly by 90 degrees or location.right, it'll actually employ the turn method twice. The critter interacts with other bugs. You'll see this in the last chapter after you're familiar with all of the classes. And it has a very interesting way of interacting. It doesn't eat other critters and it doesn't eat rocks but you can certainly make subclasses of critters that do. And rather than having you change the act method like we did with bugs, the critter's act method will call 5 other methods that you do modify. First, it gets all its adjacent locations. Those are the 8 around: up, down, left, right, and diagonal. If there's anything in there that's edible, it'll tell those things to remove themselves from grid, simulating eating it. And then among those locations that are available, they don't have another actor, it'll move to that location. And if it turns out to be surrounded, it doesn't move or turn or check. Again, code for this is in C4 through C6 of your quick reference guide. Here's all of the code, my goodness. So here is the act method, and you're not supposed to mess with this. If you mess with this, you probably should not be extending a critter. Critters are designed to all have the same act method, and all you have to do is change the actors that it's interested in by changing the get actors method, or maybe what it does with the actors. For instance, the process actors you might want to overwrite, or perhaps the possible places or ways that it can move. You might want to alter the get move locations and write your own. And of course, selecting which one of the ones that you got, you can also change that. And then finally, the make move. This is the make move is actually something that's in a that you can alter as well. A subclass of chameleon, to demonstrate how you can do so, you're given the code for this. All it does is it works like a critter, except that it changes the color of itself to one of its neighbors, and it does so randomly. So it's good to take a look at how you can pick randomly from a list of possibilities. C6 is where the code is, and here I got a little picture of it. So you'll notice that a chameleon critter is a subclass of critter, and it doesn't have much to it because all it needs to do is alter 2 different methods: the process actors method and the make move method. After it does what it needs to, it actually calls the default make move from its superclass with the super.makeMove. So you don't have to rewrite or copy or paste, you just write super make move, and then it'll just go ahead and execute the code that it normally does if it were just an ordinary critter. Well, in order to make all these changes, you have to know how to interact with the world, and of course the world is described with the location class. And it's important to know that all of these things have an orientation where north is considered the int 0, south is the int 180, east is 90, west is 270, and you get some static relative angles like left and right. In case you ever forget what's positive and negative, it's probably best just to refer to them in terms of these constants. But of course, if you're going to use one of these constants outside of the class, and usually you are, you have to specify not just north, but location with a capital L dot north. Remember, that's the name of the class. You don't need to make an instance of location in order to get to use one of its constants, like math.pi or something like that. And there's, of course, other constants like north and east and south and southwest, all of which are also defined. B1 is where to look in your quick reference guide. Here's an example of using it. You might want to have your bug or your critter change the direction. So you would use the change direction method. And of course you want to know where your direction is. So you can use the actor's get direction method. And then add to it. Both of this returns an int, that returns an int. And so the direction, when you're setting a particular direction, it's going to be an int, where 0 is north. Here it is with all of the interesting methods that you get with location. Like if you want to know the row, get the row. It just returns the int describing which row it's on. It'll actually tell you another location to the up, down, left, or right if you specify the direction. You can then even get the direction based upon another location to know what angle to turn it to. And of course you can compare two locations, whether or not it's equal to, or you might want to sort them by location using the compare to method. Well, let's take a look at actors in general. All these bugs and critters have a lot in common, and so they wrote a superclass called actor. So a lot of times, whether it's a bug or a critter, you'll need to know some of these actor methods. For instance, we were just mentioning setting direction and setting location. Here's a handy one. A lot of times you need to have information about the grid that your bug is on, and in order to do that, you ask get grid so you can get access to all of those grid methods. Other things are more trivial, such as color. We'll talk more about it, but rather than interacting directly with the grid, Actor World processes in a dynamic way every time you press step or run, and so it's best to put yourself in grid or remove self from grid as a way of interacting with either adding something or removing something from the grid world. There's a few preconditions. For instance, the move to. If you want to move to a location, make sure that the actor is belonging to a grid that's been added to a grid and not been removed. Also, too, the new location that you're specifying is a valid location, that you try to move to a place that actually exists. There's another precondition to worry about with the put self in grid. Of course, you can't already be in a grid, and of course the place that you specify is a location. That location has to be a valid location in terms of the dimensions of the grid that you're trying to put yourself into. Finally, you have to make sure before calling remove self from grid that you haven't previously been removed, and that makes us have to be very careful not to do things before it's too soon. So you have to know the correct place to remove self from grid so you don't accidentally try to do that twice, because if it's not in a grid and you call that again, you'll end up having a runtime error. Here is a bug, and it has a couple of specific things. It inherits all of those actor methods, but it also has the act method, can move method, the move direct method, and the turn method. And we can play a few exercises with those, altering what move does or what turn does, or perhaps altering when you can move. Make sure that you realize that if you're changing act, that you're doing so for a bug. It's considered bad form to do that for a critter. And also, don't forget, if you want to make just one adjustment to the act method, you can do that one thing and then employ the super.act so that it behaves as it would normally if it were just an ordinary bug. Putting and removing, again, is possible with the grid, but frowned upon, causes runtime errors because of the grid world animation. So you always want to use the put self grid and remove self from grid. It's a little bit silly that even if something else is going to consume you, you have to be told to remove yourself from grid. The other outside critters won't be able to directly kill you. Instead, they give you a message to kill yourself. Very unfortunate. Here's one of the things you're asked to do. For instance, here is a bug that does a Z pattern. So it keeps track of how many times it's turned to know what direction to turn in, so it makes this Z pattern. You could do other things too. Here, our class a few years ago wanted to have bugs drop mushrooms, and why not make them poison mushrooms? So the mushrooms will expire after a couple of turns, but if one of our bugs consumes a mushroom, it'll first turn black and then pass away. You'll notice too, this green bug is going to consume the red mushroom here. He turns black for one term, and then he'll actually have a little tombstone. Aw. Now it looks like we have another death here, and now the red bug seems to survive, leaving a trail of mushrooms. But again, the mushrooms themselves, unlike flowers, they keep track of how long they've been around, and they remove themselves from grid after a certain turn, and that way they won't fill up the grid too quickly. That was a fun little exercise. Again, only adapting the code that you get from the bug class. You can get some interesting things going on. Here we've adapted a critter. So these blue missiles are set to hone in on the direction of planes, and the planes will explode, and we made an explosion class that will change color, so it gives a nice animated effect. Here, I'll animate this now. So the cloud will first burst into the same color as the plane, and then darken and then lighten before removing itself. You'll notice too how these missiles will turn direction using the get direction toward method. So these methods can be used very simply to have some pretty complicated behaviors. So let's return to the box bug. I have a problem with that. It must be a tongue twister for me. The box bud only has two things to worry about that bugs don't. It needs to keep track of what step it's on, and it needs to know the maximum number of steps. And then behavior, all you have to do is overwrite the act method to update your steps, to alter turning so that it turns twice, so you get 90-degree turns, and to reinitialize the count of steps whenever you do turn. Critters are very distinct. In Chapter 4, we make quite a few critters, and they tend to eat flowers and bugs and other things, but not other critters. Not by default, anyway. You can certainly make a cannibalistic one if you choose. But you're told quite explicitly that if it's a critter, it works by calling in a certain order these 5 methods. Getting actors, getting move locations, processing actors, selecting the move location, and then making the move. You do not touch the act method. That's a no-no. You do for a bug, but you don't for a critter. Instead, you have to change these things, and there's certain things to do and not do. The post conditions are quite specific if you read the details. Changing the state of an actor is a no-no most of the time. There's only certain times and places for you to change the state of yourself or another actor. For instance, when you're processing actors, giving the list of actors that are around you, by default anyway, you can always change that by altering the get actors method. But usually when you process actors, that's when you could tell an actor remove self from grid, to tell them that you're going to be consumed. Make sure that the location of the critter is not altered during process actors either. That can throw off the processing when we animate as well. Now the select move location, it'll remove it'll set where to go next, and it's fairly important because this is the actual action that will tell yourself whether or not you're going to be dying this turn. You're not going to be removing yourself from grid in this case. Instead, you alter select move locations to a null if you want to remove yourself from grid, or else if you want to stay where you are, you still have to return something, and what you return is your current location. Finally, the make move is the method that you can change the state of the actors. That's allowed. And use the move to update state. And again, this is another place. If the location is null, that's when you remove self from grid. Remember how I mentioned you can only do this once, so it's very important that you don't do it under the select move locations. Instead, you just pass along a null. And then finally, when it gets to the make move stage of animating, it'll notice that the location is set to null, and that's when the remove self from grid should happen. Horstman, who wrote the Grid World, made these post conditions in a nice little summary, and that's what I had in the last slide. Here, the chameleon critter, we saw that changes two things. The chameleon, actually, we didn't see the chameleon critter. Chameleon critter, I should just mention, works just like a critter, except that it changes its color. So it doesn't actually have to do much. It just has to inherit everything and then just alter the process actors, because it needs to select one of them randomly to set its color. And then the make move is also, we like to go towards the direction that we're going. So normally, by default, critters can move up, down, left, right, but they're always pointing in the same direction. And if you notice in that movie, that blue critter was always pointed north. The chameleon critter has one other behavior that's slightly different. It actually will turn itself in the direction that it's moving, so it looks like it's actually following its nose, the way critters usually do. I shouldn't say that. Critters usually don't do that, but I meant the way beasts and other animals usually do. Sorry about that. All right, so we usually like to get the actors grid using the get grid method, and the reason why is we'll need to know a lot of things, like the occupied locations, and from there we can figure out what kind of objects they are using get. So very often, once we know the location, we can use the get method to get the actor, and from that we can tell the actor or ask the actor questions about itself to see whether or not we're going to be, for instance, it's finding out its color. So we can set our own color to it, or perhaps to see if it's of instance of the kind of class of the objects that we like to eat, if it's a mushroom or if it's another bug. Very often we need to know the locations of the neighborhood, and very often, of course, we want to just find out the locations of things that have something in them, and so perhaps getting occupied locations might be a better one. And of course, locations can be off the grid or completely bogus, so we often will be using the isValid method as well. The put and remove we don't use too often, and that's because we most often use things like put self in grid or remove self from grid, or ask another actor to remove themselves from the grid. If you're curious about efficiency, I found this somewhere. Someone worked out that most of these things operate very linearly. The exceptions is the toString. If there's more things to return, it'll be slightly longer time based upon how many rows and columns or how many actors are there. Not that important. When things are put into them, it's important to realize that exceptions will be thrown, and if you do something that's wrong, you might see one of two things. You might see an illegal argument exception, and that's if you're trying to move to a location that's not valid. Or the other thing that might happen is a null pointer exception. Sometimes if the object itself is null, you try to remove nothing, that will also cause a runtime error, throwing an exception. So that's more important when you're actually debugging your own critters and bugs. Because usually, if you're defining behavior, you're not going to be using the put method. You're going to be using the put self in grid. Here, this is from a bug. The bugs, when they drop a flower, they create a flower of the same color, and then they just tell the flower, hey, put yourself in the grid that I'm in, at this location that I used to be in. And of course, if you're using a critter, here's an example. We're processing actors for critters. This is how it eats everything. It first checks to see if it's a rock or another critter, and if it isn't, it'll tell, hey actor, you must be something other than a critter or a rock, so you get to be eaten by me, and so go remove yourself from grid. Grids themselves have some interesting methods. We mentioned a few of them. Some of them we get because we're usually on a bounded grid. It's actually defined in the abstract grid. Important thing to remember, when you get adjacent locations or occupied adjacent locations or valid adjacent locations, like to know where to move to, these are locations. These are not actors. So the only one of these, like get neighbors even, it returns locations. So it's very important to remember that a lot of these grid things all work by location, not by what actors are there. Instead, after you know the location, you can use the grid's get method to get that instance of whatever actor or object it might be in that location. Here are some things to remember. When you're making a critter, don't touch the act method. Instead, change one of these 5 methods. Also, whenever you're making actors or critters, more often than not, you need to store this, otherwise you keep asking yourself what grid you're in, or perhaps asking another object what grid you're in, because you need to know the occupied locations, and the way you do that is by asking the grid that the actor or yourself is in. So be careful. And of course, just as an extra reminder, getting those locations does not return actors, they return locations. So how do I get that into an array list of actors? This is a sample code. I first find out where my grid is and with a GR. Then I say, okay, get all the occupied locations. So this is going to be everything on the grid. So I have an array list of locations. And then I initialize a brand new list of actors. And here's a little loop so that you go ahead and fill up your array list of actors by asking your grid to get that location that's in your occupied locations and add that to your list. So this is very commonly used for a lot of subclasses of critter, where you have to get the information about the occupied locations to construct a list of different actors so that you can process those actors in the process actors method. In get move locations, again, oftentimes you'll need to get what grid we're in using the get grid method. And don't forget, don't just presume that anybody can just go where they're pointed. There might be problems with that location. So here's an example. First, check to see if it's a valid location. That's not off the grid, for instance. And here is a check that we go and look inside and make sure that there's nothing there. So a lot of times you're going to use this little code fragment just to make sure that something is both valid and unoccupied. Here's some example code. A lot of times you just want to get out of Dodge if it's not a valid location. So a lot of times if you have a certain location and it's not valid, just move, get out of Dodge. And here's another sample. If you have a valid location, you can find the next location, and don't forget to check to see if the next location is also valid. Here's some select move notation notes. And don't forget, rather than reinvent the wheel, it's always better and takes less time to use the super classes version. So this will incorporate all the default behavior so that your critter will do all the things it needs to do and interact with the world in all the ways that it needs to. But then you do something before or after this call so that your adapted critter can behave with the new behavior. Oops, went the wrong way with that. Oftentimes you're asked to do something random, like select a random critter to change your color, or maybe select a random critter to eat. And don't forget about the math-random function. If you take a look at the size of your array list and multiply it times random and then make it into int, you've now selected randomly a index from your that you can choose from your array list. So this little code fragment is a handy one that you'll be using from time to time. And again, just to remind yourself, don't use remove cell from grid any and every place, because multiple calls will cause a runtime error. So if you're in select move location, you return null. If you don't want to move at all, just return your current location. So in summary, you'll have to know each of the actors, how they move, how they act, how they interact. And the way you're going to do this is knowing how most things have something in common, and that structure has been carefully designed. And so if you know the inheritance relationships, you can find your way through your quick reference guide to do quite sophisticated things with smallest bits of code. You should know how to write subclasses and be an expert at taking advantage of behaviors that are already predefined and just adapting them. And of course, can't emphasize enough that quick reference guide. Know it now, because that way you can find what you need during the test. Good luck to you.